So hello everyone and welcome back to this channel. First of all, before beginning with the video, this video is dedicated to one of my close friends. So most importantly, this video is for him. And now let us begin with the wave optics. So before understanding what the word optics is now, let us first go with what a wave is. I'll be covering the introduction about waves in short. It is the word wave optics is derived from the two words wave and optics. It is not a sophisticated word, we can say. Both the words are simple to understand. The word wave means a wave, of course, and the word optics means related to light. So now the question might arise, how is a wave related to light? That's the thing that we are going to discuss today. So let us get on. How is wave related to light? I'll address this later in the video. But now let us understand what a wave looks like actually. So let us start by understanding the fundamentals of a wave. So I'll change this. Okay, sorry. So fundamentals of wave. The equation of a wave is written in the standard format of displacement of a wave is written in the standard format of A sine omega t plus phi, where now we can say x is the displacement, A is the amplitude, omega is the angular velocity, and the phi is the phase difference. We'll be covering this content in really short time, so hold on tight with us because this is a very fast journey now. So this is a standard equation. You might have seen this equation. You should have seen this equation in SHM. That denotes a wave. Sorry. This denotes a wave. So now that we know what a wave looks like, I'll just draw a quick rough sketch of what a wave looks like for the people who don't know it. This is all that you have studied in your previous chapters. So now let us get going. And I'll take another color, and so this is a wave equation, and this is what it will look like. As it is a sine function, so the function would start at 0 on 0, but it depends upon the phase difference. So now let us understand the type of interference that occur in nature. So there are two types of interference. I'll write down it on two contradictory sides so as to understand. One is constructive interference and the other is destructive interference. So now what is a constructive interference, you may ask. So constructive interference is where both the crest of two waves or trough trough of two waves come together, and here is the contradictory. Here one's crest and other's trough come together, or here it may be trough and crest, we can say. So in this situation of constructive interference, the part differences, we can say, we have derived it in the chapter of waves. So now the part difference is an integral multiple of lambda, while over here in destructive interference it is an odd multiple of lambda by 2, whilst the phase difference here is an even multiple of pi, and over here the phase difference in destructive case is an odd multiple of pi. So these are some important things that we have to remember, essential conditions that we just have to know at any cost in order to understand the chapter of waves. Just a minute. Okay, so now let us move further and understand. Now that we have gone through the types of interference, so now let us understand the basic question that we all have right now, that is light a wave or a particle? Wave or particle? So now some of you might have heard about this debate of dual nature of wave, dual nature of light in atomic structure, or even in Einstein's photoelectric effect. But that is not the complete story that we have to know. So now it doesn't tell, the photoelectric effect does not tell about the complete story. Instead, it deals with the material sciences. So now we have to understand what the light is. So let us go back into the principle of waves again and understand an important point that gave us a little bit of hint that light may be a wave. So there was this scientist called Eugene, Huy. I also get the spelling wrong every time. Huy gene principle. So what does Eugene's principle state? Every point on a wave acts as a secondary source of disturbance. So now let us understand this by getting a diagram, and to realize this we'll take a very beautiful example, a wonderful one. So there is this lake that we are seeing through, and here our eyes are. These are our eyes on the top side. Here our eyes are on the top side, and now we are seeing through here, and yes, there is this small particle in over here that is going up and down. So in order to see it, I am drawing another diagram on this side to show the movement of the particle that is happening. It is first initially over here. I'll draw a bigger diagram, and it is then over here. So it is doing SHM for a simple understanding. So what will it do? It will propagate a wave, a disturbance. So if we see from this side, the wave would look something like this. And I'll continue the wave over this side. But if we watch it from the top side, it is like this. So this is a crest, and then there is this trough. We are assuming it as a trough. Again a crest, again a trough. Just a minute, these annotations are a bit wacky. Then again a crest, then again a trough, and so on. So now what we are seeing is an interference pattern that is circular. And this is the kind of wave that we'll be looking for. So now we can say if a source having a certain specific vibrations or creating a wave is kept, then it will create a wave of some sort like this. Here, then this. So it's going in circles. These are complete circles that I'm not drawing completely, just the front part of the circles I'm drawing, and so on, and so on it would go. And if I keep a specific object within the closed limit of this wave, then it would create an interference pattern. Now this was the first wave, and now let us imagine another wave. I'll take a different color, a contradictory one. Green would be a good one. No, green is already taken. Yellow would be a good one. And there is this another wave coming. So at every point, these two waves are coinciding, and their coincidence is creating an interference pattern. And we won't be studying about all the interference pattern. So now what we can see, I'll take a specific number of points. Over here, or over here, the interference is constructive, as both have the same amplitude at that point. That is, the displacement of both the waves is the same. We can say it is maximum, or we can say both have their crest and crest, or trough and trough at that point. Here also the same story. Interference is constructive. Over here now, if we see this part, let me read it this way. So at this point, interference is destructive. So enough of this. So now you understood how a two-sourced thing can create disturbance and lead to this. So now that we have understood this and the Eugene's principle, now let us connect it back to wave. So there was this brilliant scientist called Henry Young, and he did a wonderful experiment that is also called as YDSE, Young's double slit experiment. This was one of the revolutionary experiments that was done and performed in the lab in the 18th century, that settled the debate that light was a wave at that time. But then later again, the proof started emerging in the 19th century that light is a particle, and hence to like end this ambiguity and this chaos and debate, all the scientists came together and they all unitedly decided that light is also a wave and also a particle. It acts as wave in some cases, whilst it acts as the light ray in some other cases. And there is a limit up to which the ray optics, ray optics, where the light acts in a straight line. is valid, and where the wave optics, where it acts like a wave, starts. So we'll discuss about it too. So now let us understand what this experiment was all about. So what did Henry Young do that was so revolutionary at his time? Let us get to know it now. So this is a paradise, you can see. This is capital D. I'll come to a minute. So now he took two slits, S1 and S2. You know what a slit means? It means two thin opening. So now I'll draw a paper. So here is this complete paper out of which only fine pieces are cut out like this. So now this is slit S1 and this is S1 and this is S2 over here, just right. And in between there is this gap, which is this small d denoted by. So not that small, but we can say comparatively small. So D is very much smaller than capital D. And now we have kept a source of light over here and a source of light over here at S1 and S2. And for time being, we are considering both of them to have the same, to be the same kind of sources, that are coherent sources, which have a path difference of 0 and a phase difference of also 0. So these are coherent sources which Young's experiment actually had. And now if the part, I know they are not right here, they are just behind S1 and S2. So now if it would have been, the light would have been a particle, it could have, let me take this things a bit back because it wasn't that close. So over here and over here. So now what Young said is that if light would have been a light in a passing like a ray, then over here the light would collide and there would be no image on the screen, whilst light would go in a straight line over here in a straight line, over here in a straight line, and over here in a straight line. And so there would be two bright spots formed on our screen, that is like this. I am denoting these as the bright spots. But this is not what we actually found. It was something completely fantabulous. So what we understood was that if we perform this experiment, I am drawing the diagram again in order to understand this and compare what the differences were. So this is our diagram, this is our capital D again. And this is our D, capital D. This is our screen. Now this diagram is very important. That's why I'm drawing it very carefully. And this is the distance between the slits. And now, if we see right now, if we perform this experiment, then the result was not this. The result came out to be different. The result was something like there was an interference pattern. Now the word I'm using, it's very important. So now I'm denoting the bright spots like this. This is a bright spot. Again, this is a bright spot. Again, this is a bright spot. This is a bright spot. This is a bright spot. this is a bright spot, this is a bright spot. Something like this interference pattern was observed. And hence, in order to answer the question of how this was observed, we prove that the wave is acting, the light is acting like a wave. Only then would there be such an interference pattern. That is, over here, both the waves S1 and S2, emerging from S1 and S2, emerging, these both are waves, these both are waves. So now, over here there is a constructive interference. Over here, just below it, there is destructive interference. Over here, again constructive. Over here, it is destructive interference. And now, if we see over here, I'm taking another color just to represent the change, but we haven't changed the waves. It's okay. I'm over here at this point, I'm taking this point. Over here, this wave came in, and this wave came in, and it had a destructive interference over there. That's why both the waves, and the waves were not like this, they were in the form of a wave front, which I discussed over here. This pattern, this is a wave front, this is a wave front. That's what the Eugene principle uses, every point on the wave front. So now that we have known this experiment, let me generalize this diagram once again, and now you with me draw this diagram so that you also get it in your memory. So there is this screen, this is slit 1, this is slit 2. The distance between both the screen is, both the slits is small d, and the distance between the screen and the slits is capital D. So now we observed this point which we expected to be as dark, the centralmost point was bright, and we assumed it as central bright. Now we'll get the story right now. So how did the name central bright come to it? So we have assumed this D over here, and so now what happens is we take the point exactly over here in the center of D and put a perpendicular on the screen. So putting a perpendicular on the screen over here, okay, putting a perpendicular upon the screen at this point. So this point is C. Over here, both the waves coming from slit 1 and as well as slit 2, I am writing now at S1 at C, distance travelled by, I'm not changing pens actually, distance travelled by S1 is equal to distance travelled by S2. That means both have travelled the same distance, so their path difference is equal to 0. So in this case, the path difference is 0. So we define the point where path difference of both the waves is equal to 0. The point is central bright. And now For the path difference, now let us see the diagram. Let me assume this as theta, and hence, and I am putting a perpendicular from S1 on S2. Okay, only one line. That's just a heck lot of lines. Perpendicular from S1 on S2. And so now, if this is theta and this is 90, so this must be 90, and the sum of the interior angles, so this angle plus this angle must be equal to theta, but the sum of the angles, so I am writing it over here. So let this be alpha and beta, and so alpha plus beta must be equal to theta, but alpha plus beta plus 90 degree is equal to 180 degree, so alpha plus beta equals to 90 degree, so beta equals to 90 minus alpha. And now this is the first condition and this is the second condition. So putting beta in the equation, so it is alpha plus 90 minus alpha equals to theta, so alpha cuts and theta becomes 90 degree. So in this case this is 90 degree. What this means in this particular case? So the path difference is equal to 0. That means if this is d and this is alpha, then this length, extra length, let me just select this as not that important. I'll delete. So now if this is d, now that this is d and this is alpha, so this length is, we use opposite side, this is 90 degree, so opposite side upon hypotenuse, that gives us sine alpha is equal to opposite side s2, let us give this a name m, s2m upon d. So s2m, that is the path difference, the extra length covered by s2 to reach c, is d sine alpha. Let me write d by this denotation so that we don't get confused. So delta x equals to d sine alpha, and now as the angles are very small we can convert sine into tan. So this is tan alpha and this is d equals to delta x, and now by geometry we can prove that alpha is equal to theta, and hence as alpha becomes theta, so we can write delta x equal to d tan theta, and tan theta is d upon this distance, and we take this distance from c, so d into 0 is equal to delta x. So we are measuring all the distances from the central bright, hence the distance of central bright from the central bright itself is 0, so the delta x becomes 0, and we proved. So now let us take a general case wherein the wave is just traveling, where it has traveled to a random point y, to a random point. So let this be d, this is s2, this is capital D, and now let us take this wave coming over this point. No, these are not straight. Okay, so let us assume this C to be over here and the distance between these two is y. So now let us now apply theta. This is also theta and this distance is also theta. So now this is the point where delta x is 0. As this is theta, we put a perpendicular as we did the last time. This is 90 and now this is theta and this becomes theta. This is 90 again. This is theta and this is theta. So theta plus theta must be equal to, alpha plus beta must be theta as we proved earlier, and alpha plus beta must be equal to 90. So beta must be 90 minus alpha. Yes, we can prove it now. So the sum of the remote interior angles. So the remote interior angles for this, we cannot do it like that. But yes, the proof comes in and this becomes theta. So the path difference as we derived earlier was, let us apply sine in this triangle, this triangle. So if we apply sine, then sine of theta becomes S2m, that's point bm upon d. So the path difference becomes d sine theta, and S2m, I'll write it as path difference, is sine theta. Sine theta is approximately equal to tan theta for very small angles. So I'll write over here tan theta. And the tan theta in this triangle is, in this triangle, I'll see in this triangle. In this triangle, tan theta is y by d. So I'm writing it d into y by capital D is delta x. So not for getting confused by dy for differentiation, I am writing yd upon d. So for a point to have, for location of bright spot, what does a bright spot mean? It means constructive interference. So for constructive interference, we say the path difference must be equals to integral multiple of lambda, that is yd by d must be equals to m lambda. So y must be equals to n lambda d upon d. So this becomes a condition for a spot to be bright, and over here n starts from 0, 1, 2. So if they ask us about the first bright, then we put n as 1. If they ask about the central bright, then we put n as 0. Now they ask us about the darker spot. So if they ask us about the darker spot, then the path difference must be an odd multiple of lambda by 2, that is yd by d must be 2n plus 1 lambda by 2, and Now solving y equals to 2n plus 1 lambda by 2 capital D by D. We'll continue further this.